speak here today. I'm going to be giving a kind of survey, so I'll apologise from the beginning that it's going to be kind of skimming across the surface of the whole topic. And I guess it's appropriate. I'm reporting on some correspondences between black holes and supergravity string theory, and stuff about qubits and entanglement that we've just been hearing about. Yes, what else do I want to say? Yeah, I normally am talking to high energy people and they don't necessarily know what a qubit is. So I realise I'm now faced with QI aficionados, and I maybe have weighted the material slightly wrong because of this. But so you might be a little bored at the beginning, is what I'm trying to say. But maybe you'll enjoy hearing stuff you already know. Who knows? Okay. So I guess the other thing I want to begin by saying is that everything that I'm talking about is it's a mathematical correspondence. We don't have any physical understanding of why there should be any relationship between the two subjects in the way I'm presenting now. Though maybe there is. And I guess the philosophy we're taking is that, despite this, it's useful to look at this correspondence and try and learn things about either side of the picture. Okay, so as I said, I'm going to be talking about quantum entanglement. I don't think I need to tell you guys that this is a key topic in the world of quantum information theory, both from a foundational and a kind of quantum computer perspective for these reasons. And I'm also going to be talking about black holes. So in the seemingly separate world of black holes and their entropy, big things have been happening, and they're meant to give us clues into the theory of quantum gravity. I guess, depending on your philosophy, you can say this is right or wrong, or we're not ready. But anyway, people have been using black holes to try and understand quantum gravity for quite some time now. And as I've already said, I'm going to be discussing a correspondence between these two subjects. In particular, I'm going to be talking about black hole entropy and quantum entanglement, and this is the kind of the central example. Maybe this basically sums up the kind of core of the whole idea. We have that the measure of tripartite entanglement of three qubits, Alice, Bob and Charlie, known as the free tangle. This was introduced by Kaufman, Kundu and Wouters some time ago, is related to the entropy of a particular type of black hole in a particular theory. This theory is called STU model of supergravity. It's in 4 dimensions. It emits black hole solutions, and they have a well-defined entropy. And we have this equation. This is the black hole entropy. This is the free tangle, parameterizing the amount of entanglement. This is the mass. Okay. And in fact, the free tangle and the black hole entropy are both given by what's called Cayley's hyperdeterminant, which he introduced in 1845. So that's where the link initially comes in. And once you've made this observation, you might ask, well, what does this give us? Can we generalize it? And I guess I'm going to spend the first part of my talk explaining this link, and then the other part explaining, the generalizations that you can develop. So the key generalization is extending to this what is called n equals 8 supergravity. I guess this is, if you're not familiar with supersymmetry and stuff, this is not so important. What's really important is to just know, or just trust me, that this is kind of the maximal case for the supergravity. The other supergravity theories can be thought of living inside this one particular one. So generalizing to this case should give us a lot of generalizations. It should help us recreate all sorts of other examples. And I want to point out that basically my talk is based on this review. This is work done in collaboration with fellow PhD students, Deminda here at Imperial, Ajay Ibrahim, who's now at Brandeis, PhD student here, Will Rubens, and our supervisor, Mike Duff, who's also at IC. Okay, so that's a plug. Right, so the outline, if we'd organised this better, if we somehow knew how this was going to go, I think maybe we'd have put me first, because I'm going to spend some time talking about SLOCC, and it might have been useful for you to have all of that laid out. You could have just jumped straight in. Okay, Okay, so I'll start with that, and that, as I said, I apologise if this is slightly old hat, but maybe it's new, I'm not sure. And then I will very briefly describe black holes in the STU model before moving on to the central idea, the entropy entanglement correspondence. And I'm going to talk about this from a particular mathematical framework called the Freudenthal triple system. And yeah, but we'll get to that when we get to it. And then I'll talk about the n=8 generalization, and this will come with some further developments, including trying to understand the microscopic picture. So for the first part of the talk, I'm going to be talking about black holes and supergravity, which are, you can think of essentially as classical. And then I'm going to turn to, all these black holes are meant to have a stringy microscopic picture underlying them, and then you might ask, well, if this is the case, can we connect the microscopic picture to the qubits? And that's what I'll talk about here. And then I'll just talk about some additional stuff that's ongoing now. Right. So, to begin with the SLOCC paradigm. Okay, so we had LOCC stands for local operations and classical communication, and I guess basically the idea is that you want to have experimenters in their spatially separated laboratories, and they're allowed to do whatever they like in their laboratory, and they can communicate any results or any protocols or procedures they do, and discuss it with their collaborators across the other side of the world, as long as this communication is classical. And we kind of take this, by doing this, it kind of intuitively seems that you should be able to establish any classical correlation, and conversely, that you should not be able to create any genuine quantum correlations by the nature of these operations, i.e. entanglement. So the key message is that Locke cannot create entanglement. Okay. So then you can use Locke or SLOC, as we've heard already. SLOC is stochastic local operations and classical communication, to try and understand different types of entanglement. The basic idea is that you say two states are SLOCC equivalent if and only if they may be interrelated with some non-zero probability by local operations and classical communication. So if they may be interrelated, obviously these operations must be invertible. That's why your full class of LOCC operations gets reduced down to this invertible subset. And because it's interrelated, they must have the same entanglement. Locke cannot create entanglement, so if two states are interrelated to each other, they must have the same entanglement. So we find that that equivalent states should have the same entanglement. So if you can consider, this idea was introduced in this paper. So the set of LOCC operations that relate equivalent states kind of form a gauge group with respect to entanglement. They throw away the information that you don't care about with respect to the non-local properties, and so you can think of it in that way. And they, Sirek, Durham, Vidal showed in their paper that two states are SLOCC. An n qubit state is SLOCC equivalent if they can be, two n qubit states are SLOCC equivalent if they may be related by this n times tensor product of the group SL2. Okay. So the basic idea to understand different types of entanglement is you take your state space and your SLOCC equivalence group, and then you form this coset space here. And now, naive parameter counting implies that you have this many the minimum number of complex numbers needed to describe this set of orbits is given by this equation. This is why you see the transition between 3 and 4 occurs that you described. Because for 3, this equation stops making sense. So this is some kind of finite set of orbits. And we'll spend some time understanding exactly what that finite set of orbits is. When you go to 4 qubits, you're going to need 4 complex parameters to parameterize the orbit space. So it becomes a much harder problem. Okay, so the 3 qubit example is what we're going to concentrate on, and we just have this 8-dimensional Hilbert space. We denote our state vectors in this way, and then this is our space of entanglement classes or orbits. And as I said before, the naive parameter counting suggests that we ought to expect some kind of discrete set of orbits, which would make the entanglement classification particularly simple and concise. And indeed, you do get this. Sirac-Vidal showed this in 2000, and Miyake and Wadati also had some similar results relating to this onion structure. So here are the different classes. So there's the tripartite entangled classes. There's the GHZ and the W. Then there's the bipartite entangled classes where you can pull out Alice, but Bob and Charlie are in an EPR pair. And then there's the completely separable class. I'm not really sure why we've included the null class where there's just no state, but we have for completeness, I guess. Okay, so here's some representatives. This is totally separable. This is biseparable. You can clearly see that you can pull out Alice out of this state. This is the W state. It's the same one that we had in the previous talk. And I've put robust to mean the same thing as you meant, where you trace over one qubit and you're left with something that's maximally entangled, or at least a mixed state, a generically mixed state that is maximally entangled under many criteria, being more generic about the whole thing. And then here's the GHZ state. So this is the one that Merman used to, conjure up his weird non-local examples, violating local realism. Okay, so the next question is, these are the different orbits. These are 6 classes. And the next question asks as well, how do we distinguish these orbits? How can we tell whether we're in a separable state or actually in a GHZ state? And so to do that, we introduce what are called the 2 tangles. So I'm not sure if this is the diagram I actually wanted here. Anyway, the 2 tangles are kind of describing the entanglement of Alice with the Bob-Charlie system, for example. And then equivalently, there are 3 of those, so the Bob with the Alice-Charlie system and the Charlie with the Alice-Bob system. And then there's the free tangle, which measures the genuine freeway entanglement. So, it's ready that they're all entangled with each other. So the separable class is just given by all the 2 tangles vanish. So you just compute all 3 2 tangles, and if they all turn out to be 0, then you know you've got a separable state. Similarly, for the biseparable, you just have 2 non-vanishing 2 tangles. For the W state, all of the 2 tangles are non-vanishing. So, in a sense, each qubit has some entanglement with the other pair. And then finally, the GHZ state has non-vanishing free tangle. And as I said before, the free tangle is actually given in terms of Cayley's hyperdeterminant. Miyake and Wadati pointed this out, which is this kind of complicated looking function of the state vector coefficients. Well, essentially it's just the unique SL2 cubed invariant. In addition to being SL2 cubed invariant, it's also invariant under the interchange of A and B and B and C. Okay, so that's that. And then you get this entanglement classification. So this is your class of totally separable states, and you can see this basically summarizes everything I've just been saying. So the other thing that you could consider is just standard lock classification of entanglement. In this case, we say 2 states are equivalent if they can be related by lock with certainty. And it was shown some time ago that this is only the case if they're related by local unitaries. So, and in particular, the free qubits lie in the set are 2 free qubit states are LOCC equivalent if they may be related by, this is a typo, the global phase is right here. I don't know why I've put this here. If they may be related by this group. The fact that you don't have free U2s boils down to the fact that actually the parameters corresponding to each of the U1s are not independent. Okay, so you get that, and this gives you a more, when you look at the space of entanglement classes under this classification, you're checking out this guy, and so the minimum number of parameters required is 6. This is just, you know, taking the 16 dimensions of the 16 real dimensions of this space minus the 10 real dimensions of this group, and that gives you the minimum number. And in fact, you can prove for 3 or more qubits that this minimum number is actually saturated. So it's always the number of parameters needed to describe the class of the orbit space, or the entanglement classes. It's always just given by this minus this. Equivalently, we could ask for algebraic invariants under this group. So you need 6 independent algebraic invariants in order to parameterize this space. And they are the 3 tangle, the 2 tangles, the norm, and the Kemp invariant, which I'm not going to say anything about because we don't really need to. But for our comparison that we're going to make later, we're really interested in states with real state vector coefficients. So I said I should point out there are a number of differences. And this is one of the differences in the black hole picture. We want our state vectors to be real. So we're imposing this condition now for future use. And this is, you find that your Hilbert space is reduced to this, and here is your LOCC group, and your parameter counting now becomes 8 minus 3 equals 5. And these invariants are given by the hyperdeterminant. These are the local entropies, which are just related. They're basically the 2 tangles I introduced earlier, and the norm. Okay, so you get 5 parameters. 5 parameters are needed to parameterize the most general state, and then from that you can produce any other state using the SLOCC equivalence group. And this is pointed out by Asin. And here I've written it in a kind of, well, for our purposes it's conveniently written, maybe for other purposes it's not conveniently written. So there's just n0 through n3 and an angle theta. We'll see why that's convenient for us later. So that's the most general real 3-qubit state. Okay, so now onto the other side of things. So it's a bit of take a bit of a turn, and we're going to talk about the STU model of black holes. So the STU model is, it's supergravity coupled to 3 vector multiplets. Here's the Lagrangian. I'm not really sure why I've put that there. I don't. No one's going to get anything from that. Maybe I was worried someone wouldn't believe it existed. I don't know. But there it is. Make of it what you will. Sure. What's important is that the U-duality group, I'll say some words about what the U-duality group is in a moment, is SL2R cross SO2, 2. So the U-duality group in M theory in general is you can discuss M theory on different, for example, different geometric backgrounds, and it can happen that the string theory that you get on 2 different geometrical backgrounds actually coincides. So you have this symmetry relating different, what would a priori be different string theories, but they're actually related by the symmetry called U-duality. Now, for us in this picture, what this corresponds to for us is this is just the symmetry of the equations of a motion of the Lagrangian of the last side. So supergravity is the low energy limit of string theory, and the U-duality group just becomes the symmetry of the equations of motion. Other important things about the STU model is that it has 4 field strengths plus their joules. So when you're looking at black holes, you get 8 electric magnetic charges, so 4 electric, 4 magnetic, coming from the 4 field strengths plus their joules. And what this means, so we're really considering the class of extremal black holes. Extremal charged black holes satisfy the charge mass equation. So basically, just think of it as the Reisner-Nordstrom black hole. You have a condition for it to not be a naked singularity, that the mass must be greater than the charge. Yeah, and And when we say extremely, we just say the mass is equal to the charge. So really, we've kind of, and what happens in that case is that the whole black hole solution is determined just by the charges. So the most general, extremal, static, spherically symmetric black hole appearing in the STU model is completely determined by these 8 electric and magnetic charges, which are, these are the electrons, Q's are electric, P's are magnetic. And however, the generating solution just depends on 5 parameters. So you take 5 parameters and add in the new duality group, and you can create any solution you'd like. So the next thing is the black hole entropy. Now Hawking told us this was given by the area of the black hole. The area is given by the mass, and for our extremal black holes, the mass is given in terms of the charges. So what's really important for us is that the black hole entropy is just a function of the 8 charges. Maybe I should say some words about the attractive mechanism. So there's these scalars in this theory. There's a whole bunch of scalars in this theory too. And a priori the black hole entropy could depend on these scalars, and this would be a bad thing because we need, for the entropy to be a physical quantity, it needs to be U-duality invariant. And if it depended on the scalars, it wouldn't be U-duality invariant. But miraculously, we have something called the attractor mechanism, which fixes the scalars at the horizon of the black hole in terms of the charges, so this problem doesn't ever arise. And then you just get your entropy is given by this quartic polynomial in the black hole charges. So I think I've said everything I wanted to say about the black holes, and now I'm going to make the correspondence between the hyperdeterminant and the entropy. I think I've set it up so that it's perhaps a bit obvious what the next slide is. Oh no, you wouldn't have guessed that. I didn't guess. So look, this is telling us what the next slide is going to be. Okay. So here it is, the entropy and entanglement. We can identify the charges of the black hole with the state vector coefficients using this dictionary, such that we find that the entropy is given by Cayley's hyperdeterminant of these state vector coefficients, which is precisely related to the free tangle in this way. So this is what my supervisor pointed out in 2006. That's it. So, okay, now we've discussed that. If we just left it there, then perhaps it would be a bit boring. So the rest of the talk, I'm going to try to develop this idea a bit. And we're not the only ones trying to develop the idea. There's other groups working on this. Well, I say other groups, 2 other groups working on this. 3 other groups maybe at maximum. So Peter Lavoie made some connections between the attractor mechanisms and optimal local distillation protocols on the QI side. And supersymmetric black holes and non-supersymmetric black holes corresponded to the suppression or non-suppression of bit flip errors in these particular systems. And he's also, with some clamp from some finite geometries in Germany, he's been working on connections to the Pauli group in finite geometries, which I'll try to say something about later. Although at the rate I'm going, I'm not going to have time. So I'm not going to tell you about that, I'm just going to point to this reference, and you can find out for yourself if you're interested. What I'm going to tell you about instead is I'm going to kind of, really go through the whole connection more explicitly between the STU black hole and the free qubits using Jordan algebras and Freudenthal triple systems. So basically, for a large class of supergravity theories, the most elegant way to describe the black hole solutions is to use a Jordan algebra. And then when you dimensionally reduce down to 4 dimensions, it so happens that the most elegant way to describe the 4-dimensional black holes is to use what's called a Freudenthal triple system. Now, a Freudenthal triple system is a vector space that just contains the Jordan algebra of the 5-dimensional theory that your 4-dimensional theory came from. So in a way, it's kind of a nice, consistent picture. I might skip the Jordan algebra stuff, and you just have to trust me about everything else I said. So, as I was saying, this is our FTS is a vector space, and you construct it out of 2 copies of a Jordan algebra and 2 copies of the field that Jordan algebra is defined over. And apparently, Brown wrote about this in 1969, and Faulkner seems to have written about it in Faulkner, according to BibTeX. And Farrar has written about it in Farrar. Luckily, Freudenthal wrote about it in 1954. Okay. So yeah, you can write an arbitrary vector in this space as a kind of 2 by 2 matrix. Here's an example. So we just have alpha and beta just belong to the fields. They're just scalars. And then A and B are the Jordan algebra elements. Now, this FTS comes equipped with an antisymmetric quadratic form, which we denote by these curly brackets. These traces and these ends and these hashes are all operations in the Jordan algebra that I would have just told you about, that I've skipped. But it's not really important. So there's this antisymmetric quadratic form, and then there's this quartic form, Q, which is really important, and it's given by this equation. It's just quartic in the coefficient specifying your vector. And then finally there's this triple product. It takes 3 elements of the FTS and chucks out another element of the FTS. Okay? And then associated with the FTS is a group called the automorphism group. This is just a set of linear transformations that preserve the quartic norm and the antisymmetric bilinear form. And these two equations together imply that the triple product transforms covariantly under these transformations. That comes from this equation here. So here I've got a list of Jordan algebras, and then you plug this into the FTS construction, and here's the corresponding list of symmetry groups. So in particular, I'll point out this one here. This is J3O superscript S, stands for the Jordan algebra of 3 by 3 Hermitian matrices defined as the split octonions. And then in that case, you find that the automorphism group is the maximally non-compact form of E77. And this is in fact the symmetry group of n equals 8 supergravity. So, and this is generically true. You just do this and you get the right symmetry for the supergravity. It's interesting for our purposes if we have this one here where you just have 3 copies of the field. The vector space is 8-dimensional, and the automorphism group is the threefold tensor product of SL2, which by now should be ringing bells. The other thing I want to say about FTSs is that they're naturally, an element of FTS is naturally equipped with a rank in the same way as a matrix has a rank. And these are the conditions determining the rank of an FTS element. The rank runs from 0 through to 4. It's manifestly automorphism invariant, and it partitions the whole space. So this was my point that I was making earlier. It's well known, well I suppose amongst supergravity circles, that the FTSs describe the supergravities that arise from string theory and M theory. And in particular, the automorphism group is the D=4 U duality group. The black hole charge vector is an element of the FTS. As an example, we have this one I was saying earlier, where you plug in these 3 by 3 Hermitian matrices over the split octonions, you get E77 as the U duality group, which corresponds to n equals 8, d equals 4 supergravity. And then the black hole entropy is given by the quartic norm Q. So we now want to use this to further understand the 3-qubit entanglement picture. So for the STU model, we can write down this Freudenthal triple system, where this is the threefold direct sum of the field, are these Jordan algebra elements here, and these are the scalars. So your charges just get arranged in this vector in this way. And then using the dictionary that we introduced a few slides back, relating the black holes to the qubits, we can write down, we can use the FTS as a representation of the 3 qubits. Now, just churning through all the machinery, you find, as you might expect, that the quartic norm is precisely Cayley's hyperdeterminant. And I've defined these gamma matrices in this way. So these are covariant tensors under the U duality group or the SOCC equivalence group, because they'll be useful later. And so you can also write Cayley's hyperdeterminant as a conventional determinant of these gamma matrices. And to connect it to the more ubiquitous quantum information quantities see that the norm of Q is just the free tangle, and the two tangles are given by the gamma matrices in this way, where you just cycle these letters to get the other two corresponding two tangles. And then finally there's the triple product, which I said took 3 elements of your FTS and gave you out another. So if you put in a free qubit state, you get out another free qubit state, which we denote TA, the coefficients of as TABC. And this is given by these equations. These are all equivalent, and they transform as a 2, 2, 2 of the SOCC equivalence group. And this is how you recover the Kemp invariant, by taking the norm of T. And here are the ranks rewritten in with our FTS free qubit state. So, in particular, this one, well, we can rewrite it in this way. I don't know if that's illuminating to you guys, but what this implies is that when this first object vanishes, it implies all 3 gammas vanish. And then when T, the triple product, vanishes, it implies that there is only one vanishing gamma, only one non-vanishing gamma, precisely one non-vanishing gamma. And when T is non-zero, all the gammas vanish. All the gammas are non-vanishing. And then this gives us the entanglement classification. So the FTS naturally, and the ranks naturally capture the entanglement classification of free qubits. What's nice about this is it's manifestly invariant, whereas when we were talking about the local, the 2 tangles and local entropies before, that wasn't the case. Yes, okay, so to kind of exploit this machinery a bit further, we noted that because the algebra related to the automorphism group kind of decomposes quite simply into 2 copies of the Jordan algebra, I didn't describe this, the structure group related to the Jordan algebra. It's quite easy to characterize what the orbit spaces are, which we hadn't seen in the literature before, so we thought we'd put them up. And this was also interesting from the black hole perspective. So this is one of the examples of where we're learning stuff that we didn't know about the black holes before by studying the quantum information side of things. So these are called, I should have put what these correspond to in terms of black holes on this side, but I haven't, I forgot. But W, biseparable and separable correspond to what are called small black holes, and the coset spaces, which are useful objects to know in supergravity, weren't known, but we discovered them by looking at the complex case and then finding the real forms in this way. What's interesting, the GHZ state for real qubits actually splits up into 3 different classes. How will you quite interpret that in terms, I mean, there's a nice supergravity interpretation of this. I don't know what its quantum information interpretation would be, why the GHZ class should split up in this way for real bits. But it does. Okay, so now on to the generalizations. So, underlying the example, the STU model example, is the fact that the SLOCC equivalence group naturally arose in supergravity. And as I've been saying throughout the talk, in the n equals 8 case, the symmetry is E77, which is not something that you'd imagine would pop up in quantum information very, you just wouldn't imagine it would be there. There's no reason to suspect it would be there. So, but it actually turns out that there is a nice quantum information theoretic interpretation of the n equals 8 black holes. So, whereas the STU black holes were parameterized by 8 charges, the n equals 8 black holes are now parameterized by 56 charges. And whereas the U-duality group was SL2 cross SO2, 2, it's now E77. So, finding a quantum information kind of picture of this relies on the fact that because E7 is rank 7, it has 7 copies of SL2. So we can look at this decomposition, and it goes like this. So decomposing the fundamental representation of E7, the 56, and the 7 SL2s, we get these bunch of 2s and 1s. You see there's always 3 2s and 4 1s. And you can write this as a state, which maybe with a bit of abusive terminology we call the tripartite entanglement of 7 qubits. So now there are 7 SL2s and 7 associated qubits: Alice, Bob, Charlie, Daisy, Emma, Fred, and George. And you can write them as this. So this is like the direct sum of 7 copies of the 3-qubit Hilbert space. Another nice way of just capturing this structure is to note that if we look at how Alice, Bob, and Dave sit together in their tripartite entanglements, we have an Alice, Bob, Dave, a Bob, Charlie, Emma, an Emma, Charlie, Dave, Fred, and so on. And this is nicely captured by the Fano plane. So the Fano plane, so this is Alice, Bob, Dave, was that first ket, and you do it for every line. And it also turns out that the Fano plane describes the multiplication table of the octonions. So these arrows, which would otherwise be redundant, are actually telling us that when you times octonion A with octonion B, you get plus octonion D. But going the other way, D times B gives you minus A. So this is the whole imaginary octonionic multiplication table. Okay, so now we've related something that looks like some kind of quantum state to our black hole charges. And we have a 56-dimensional Hilbert space. The next question is, can we make sense of the entropy, entanglement, correspondence? So the entropy of the black hole is uniquely given by Cartan's quartic E7 invariant. These X and Y are antisymmetric 2x2 matrices. So there's 28 parameters in each, so 56 in total. These are just the 56 black hole charges of the n equals 8 model. Then Duff and Ferrara proposed that we use this as the entanglement measure. So this is very schematic because there's not enough room to write it out explicitly. These A to the 4, B to the 4, C to the 4, these are all Cayley's hyperdeterminant. One for each of the 7 copies of the 3-qubit Hilbert space. And then these are kind of non-trivial intertwining terms that relate the different direct sum parts. Particularly, you have these 7 four-way cross terms. Now, in order to establish that this actually comes out of the qubit black hole correspondence, we did this by constructing a dictionary. Here it is. It's not massively illuminating. If you're really astute, you'll notice. So these are the X. These 2 matrices are the X and Y, the 8x8 antisymmetric matrices that describe the black hole charges. And if you're really astute, you'll notice that this is also the multiplication table of the imaginary octonions, dual to the one I showed you on the other slide. In fact, this dictionary is completely specified by the Fano plane. All the signs come from the arrows on the Fano plane, and these binary indices are also miraculously described by the Fano plane as well. So the Fano plane really captures the whole of this dictionary. And it's kind of satisfying that we made this up using the Fano plane, and then we plugged it into Mathematica and compared these 2 quartic polynomials that have something like 10,000 terms, and they were exactly the same. It was quite fun to do that. And it's octonionic basis independent as well, so we did it in lots of different octonion bases. So in this case, you can actually show that the U-duality group can reduce the number of parameters down to 8 from 56. And we get this kind of summarizes the most detailed correspondence. So these are your 3-qubit entanglement classes. And these are the black holes, and you see how the amount of supersymmetry preserved for each black hole solution corresponds to which class you're in. So, yes. Okay. That's all I'll say for now. So now we've kind of discussed the n equals 8 generalization, and you might wonder, given that string theory provides a microscopic analysis of black holes, whether this microscopic analysis can be connected to the qubits in any kind of sensible way. So, we'll concentrate on the n equals 8 theory that we've just been discussing. And as I said before, this is the low energy limit of type 2a strings, all type 2b strings compactified on a 6 torus, or m theory of 7 torus. So you take string theory in 10 dimensions and wrap up 6 of the dimensions, and then you get this, and then the theory that results from that has a low energy limit, this supergravity theory that we've been discussing. Now, the microscopic understanding of black holes in this picture, what you do is you take a p-brane and wrap it around p of the compact dimensions, and then from your 4-dimensional perspective, this looks like a 0 brane or a point, and if these branes are black, then it's a black hole. So then we come to stringy STU black holes. Now, embedding the STU model in string and M theory isn't unique. There's lots of ways of doing this, but the one that we adopted, because it was useful, was to think of it as 4 D3 branes wrapping the 5, 7, 9, 5, 6, 8, 4, 7, 8, 4, 6, 9 cycles of the compact 6 torus. And then they're allowed to wrap, each of these branes is allowed to wrap one of those cycles N0, N1, N2 and N3 times. This reproduces the black holes of supergravity. You construct this model in string theory. So, in addition to those 4 wrapping numbers which parameterize these solutions, you're allowed to let the branes intersect at angles. But you can only do this in certain ways. In fact, we're only allowed to let one of the sets of branes to intersect at an angle theta. So this induces an additional set of charges, and we find that the most general black holes are then described by, once again, 5 parameters, the 4 wrapping numbers, and the intersection angle theta. Now the entropy is given by taking the logarithm of the number of microstates of these quantum mechanical D3 branes, and then you get the black hole entropy. And it agrees with the macroscopic calculations done in the supergravity theory. This table kind of summarizes what I was trying to describe in the previous slide. So this 4 through to 9 signifies the different cycles, the 6 different cycles of the 6 torus, the compact space. So it's 4 through to 9 because we're in a 10-dimensional space and we can compact divide over these last 6 dimensions. When we have an x, I'm saying that this is the first, this D3 brane here in this first column is wrapping, which way around is it? Okay, yeah. It's wrapping the 4 cycle, 6 cycle, and the 8 cycle. Yeah. So to make the connection to the qubits, we decided to split the T6 up into 3 copies of T2. You can do this, it's no problem. And then relate each T2 to one of the SL2s corresponding to Alice, Bob and Charlie. And then when we have a wrapping x0 around that T2, this corresponds to a 0 ket. And when we have the 0x, this corresponds to a 1 ket. And you immediately obtain this from that most general black hole solution, reproduces this most general real free qubit state that I introduced ages ago. So that's quite a nice picture of things. And also the GHZ state is what you get when you remove the angle, when all the D3 branes are perfectly aligned, you get a GHZ state. And this is special from the string theory point of view because it's the one state where there's no force in between these D3 branes. They don't attract or repel each other. So it's kind of like a stable state. Just as a further note, in string theory you can take yourself from type 2a to type 2b by inverting the radii of the torus that you've compactified on. And doing this, it works nicely in the qubit correspondence. You just get the kets, the 0 kets correspond to XX and the 1 kets correspond to 0, 0. Okay, so in the last 15 minutes, I will describe some further developments. I wasn't planning on having this much time left, so I won't really describe them. I'll tell you what they are and point you to the references. Okay, so the first, something that we noticed was something that we observed was that the Fano plane plays a key role in the n equals a correspondence. And the Fano plane itself has some interesting symmetries. The symmetry group of the Fano plane has 160 elements. It's a finite group, and it's sometimes referred to as PSL27. So it's like projective special linear transformations on 2x2 matrices where the elements belong to this finite field F7. And in fact, the dictionary gave us a nice way of finding the appropriate 56-dimensional representation of this group in the black hole picture. Although I must confess, I don't think we really know what role PSL27 has to play in string theory. But it's interesting that it has this symmetry. I mean, we kind of knew it from the beginning because it's a subgroup of the Weil group of E7. So, but it's nice to see it explicitly and how it's neatly realised. But then Peter Lavoie and his collaborators then did some interesting work where they kind of gave a different perspective on this whole thing. So then, rather than thinking about free qubit states themselves, they considered the free qubit Pauli group. And they related the 63 elements of the real generalized Pauli matrices, or free qubits, to the 63 points of the point line geometry of the split Cayley hexagon. Yeah, I'm not going to try to describe how they did that because it's quite complicated and it's a talk in itself. But they showed how this geometry is related to the black hole entropy via this PSL27 subsymmetry that we had found earlier. And they also conjectured that you should see the full symmetry of the Cayley split hexagon appearing in the black hole entropy. So this is given by this 12,096 element group, G22. And yes, this should certainly be true. I would believe this conjecture. What role this group plays for string theory is also, again, a bit unclear. They did go some way to illuminating this, but I'll refer you to their papers if you want to read about that. Just because it'd be nice to show a nice picture. This is courtesy of Peter Lavoie. This is the split Cayley hexagon. It's this nice pretty picture. And these coloured dots and the x, y's and z's correspond to the free qubit Pauli group. And this is how they've related it to the hexagon, diagrammatically. Okay, so that's all I'll say about that. So, as you may have gathered by now, string theory and supergravity is defined in numerous dimensions, up to 11. And you might ask if any of these other dimensions play a role. And it so happens that, at least in d equals 5, literally everything I've described, including the finite geometries, the rat brains, the whole picture goes through for d equals 5. But where you replace qubits by qtrits and d brains by n2 d brains. And then, I mean, if you want to see more details of that, I refer you to these two papers. This one deals with the finite geometry in d equals 5. There's also an alternative picture of this whole correspondence that allows you to extend it up to d equals 6. But then we get a bit unstuck in d equals 4. So we don't know which is best. We can try both. It's also given us new insights in string theory. In particular, it led us to discover a new duality for black holes, which I'm going to try to describe here. Other possible aspects that this has kind of indicated has one of them. Looking at the Fano plane, we realised. Well, let me start at the beginning. In the n equals a case, you could look at this SL2 plus SO6, 6 subgroup of E7, and then the 56-dimensional representation of E7, which is where the black hole charges live, splits under the subgroup into this 2, 12 and a 1, 32. These two groups, the SL2 and the SO6, 6, are the S duality group and the T duality group coming from string theory, respectively. So it turns out that the 2, 12 are identified as with what are referred to as the Nova-Schwarz sector. and the 1,32 with the Ramond charges. These two names just correspond to the different parts of the supergravity theory where these charges live, where they're in the Lagrangian where they come from. And it turns out that in the Fano plane picture, well actually this sentence is incomplete. In the Fano plane picture you just take a point of the dual Fano plane. This is like the STU model. Now, if you extend to a line, that takes you up to what's called n equals 4 supergravity. And this whole correspondence I've been talking about goes through for n equals 4 supergravity in a similar way. And then if you move from a line of the Fano plane to the full Fano plane, that takes you to the n equals 8 case. And we observe that going from a point to a line is like starting out with the charges being imaginary complex numbers and changing them to imaginary quaternionic numbers. And it all kind of scales up like that. So it suggests a hidden role for the octonions in N theory. If we can somehow make the n equals 4 case that just has another Schwartz leap up to the n equals 8 case by using the octonions, that would be quite interesting. For qubits, this looks rather slim. There's lots of other stuff to do with qubits, but I was running out of space in this slide. So one of the things we need to verify is the monotonicity of our proposed entanglement measure. So entanglement measures need to be monotonically decreasing functions under the set of LOCC operations. And we've gone some way to establishing this, for it's a little hard to know exactly what to define your LOCC operations as. This is in general quite a difficult problem, but it's even more difficult here. But for some sensible definition, this works, and for some other definitions, it doesn't work. So that's an interesting open problem. Okay, so I'll conclude. So we can relate STU black holes to free qubit states via the Freudenthal triple system. The U-duality group corresponds to the SOCC equivalence group. The ranks of the black holes, or the FCS equivalently, nicely capture the free qubit entanglement classes in a manifestly invariant way. And it gave us some new information about black holes, which was nice. And Cayley's hyperdeterminant gives the black hole entropy in the free qubit entanglement. It generalizes to the n equals 8 black holes, and the tripartite entanglement of 7 qubits, that's not right, qubits, via the Fano plane. You can make a sensible connection to the microscopic picture of string theory. My supervisor summarised it this way: to wrap or not to wrap, that is the qubit. It's corny. And oh look, my grand finale thing has fallen off the bottom of the slide. This sentence was amazing, but you'll never get to see it. Yes, so we were, something that you might wonder is whether you can use the algebraic machinery of the FDS to characterise other quantum information systems. And we have done some work in this direction. And so Leron collaborators, they were discussing fermionic qubits. I'm not exactly sure what that means, but it sounds like a good idea. And then on the black hole side, there are a large number of orbit classification for black holes. And if we can link them into quantum systems in the same way, it might give us the tools to classify these quantum systems. So I guess I'll finish there. Here's like a whole bunch of references. No one's ever going to write them down. Okay, alright, thank you.
Other questions?
There's some uncertainty about how many entanglement classes there will be for higher numbers of qubits and what the relationship between those will be. Is there any conjecture that suggests itself from this perspective, or would it matter what the sort of answer to that question was?
Well, I guess, I'm not sure to what extent that is actually an open question. I guess it depends on what philosophy you want to take. If you want to take the SOCC philosophy, you know how many parameters you need to parameterize the space of entanglement classes. So then it's a case of finding those invariants and then using them to parameterize the classes in the space of entanglement classes. Yeah, I guess a lot of these black holes that have had their orbits classified, it looks like they should, you know, coincide with a number of quantum systems. This is something, this is going to be, you know, future work. But it should go through for a number of cases. I would be very hesitant to say that this would provide you a general framework with which to understand entanglement. I mean, it would be nice if it did, but I'd be hesitant to make that claim.
Okay, I think you mentioned at some point that you were asking yourself why GNZ sort of splits open for real. I think that the reason is has to do with local tomography. To which extent, if you got a compound system, can you via local measurements reconstruct the state? And it's a fact that is like on the nose possible for complex spaces, and I think not for real spaces.
I mean,
and that's probably what sort of gives the fact that things start to fragment open in different tasks.
yeah, I guess that's quite interesting because, I mean, group theoretically we understand it. It's, you're looking at the real form of of the SL group splits. But yeah, I mean, so that would be a nice thing to maybe it would be a nice thing to say.
It's an axiom which a lot of people like using the axiomatization of quantum mechanics, specifically that property that with local operations you can reconstruct the state, and that actually gives the field of complex numbers.
Right, okay, so that's a motivation for taking quantum mechanics to be complex. I mean, what about quaternionic? I mean, I know...
So I think with quaternionic you sort of are over into the mind, so it's like really complex numbers which gives this nice match between local tomography and the kind of state you can have.
That's interesting. I wonder if...
Like you find this in illusion artists, axiomatizations in some implicit way. John Barrett, who's now not gravity John Barrett, John Barrett from Bristol, quantum computing John Barrett. He also wrote a lot about that axioms.
Okay.
Well, I'm sure Terry could tell you a lot about this. He's gone now.
He's not here. Yeah, I mean, that's interesting. I mean, it'd be interesting to see if those ideas say anything about the black hole. Whether, I mean, because we have some understanding of why the splitting happens physically in the black holes. I wonder if tomography can say anything about that. It sounds unlikely, but it'd be interesting to check out, I guess.
Yeah. Thirdly, would you think that by transitivity of the two last talks, there is a connection between what you could say categorical approaches to quantum mechanics and black holes?
I have, throughout my PhD...
Just say yes.
Yes, yeah, all right.
So somebody here just lost money.
Okay, I'm glad I could help you out in that way, financially, if not intellectually.
We have a bet. But, you haven't won the bet, even if you say that.
You fought that.
You must get a little job.
Okay.
Any further questions? Well,
We've got some quite big finite simple groups around,
Right, that's true.
and not just perpendicular groups.
No, I mean, that's it. There's a whole interesting story about it, and it really... The annoying thing about these finite groups is that they always kind of crop up, and then you just don't know what to do with them. Well, that's what it seems like to me. There's quite a lot of papers, at least in the quantum gravity literature, where these groups appear, and then they, you know, it's a little there's a final step that's a little lacking. So it'd be nice to really find out the role of these finite groups from the string theory point of view. I guess that's what PC avoidance collaborators are partly motivated by. There's also all sorts of connections with the octonions. You notice that the G22, so that would be, I mean, that's related to the octonions because your standard G2 is your automorphisms of the octonion algebra. And then you have this finite group, and it's in some way related to the, how do I say this? Right, so the root system of E7 is nicely captured by the integral octonions. And then you feel like this G22 should be related in some way to to those constructions. And it should all fit in together, but just how it does, I don't know.